Hello everyone, I am Shruti Kunde from TCS Research Labs, Mumbai, and today I will be presenting our paper titled GEMS, Generating Efficient Meta-Subnets. The paper is based on gradient-based meta-learner family of algorithms, which aim to learn a model initialization across similar tasks. That is, a model will generalize well on unseen tasks which are sampled from the same distribution. Some of the limitations here are input tasks in real-world applications are sampled from multiple distributions, and as a result, the similarity amongst the distributions may decrease. This leads to a negative knowledge transfer, and which ultimately leads to a deterioration in the model accuracy. You could say that we can train multiple model initializations depending on the specific task distributions, but training multiple model initializations leads to a linear increase in the training time, even though you may get a better generalization. So we see that there is a trade-off between computation and model performance. To address this trade-off, we propose two approaches, mainly the binary mask perceptron or the BMP approach and the multimodal supermask, that is the MMSUP approach. The BMP approach introduces an adapter network. The adapter network takes as input features from the current task, prior knowledge which is stored in the form of weights. The adapter network in our case is a multi-layer perceptron. It gives us an output, the task-specific learning rate, and the binary mask which adaptively masks non-trainable layers. So as an example, we can see here that the binary mask is telling us that layer L0 and L2 need not be trained for the specific task distribution, whereas L1 and L3 need to be trained. In the MMSUP approach, we go one step ahead, in which we identify subnetworks of neurons which are relevant for a particular given input distribution. So if you are given n distributions, MMSUP will identify m subnetworks for each distribution while enabling knowledge sharing between distribution agnostic parameters of the network. So as you can see, PI and PG are two distributions, and MMSUP has identified subnetworks which are specific to both distributions. The red lines actually indicate the task agnostic parameters. The green and the blue lines in this case show the task specific parameters. So identifying distribution specific parameters avoids training parameters which may not be relevant to a particular distribution, and hence it avoids in general training of irrelevant parameters in the network. Our results are very encouraging. So BMP and MMSUP both outperform the base MAML algorithm in terms of accuracy, because both these approaches identify layers or parameters which are specific to task distributions when training. Now both of them also have a lower training time as compared to multi-MAML, because multi-MAML will train a separate model for each incoming task distribution. In a cross-domain scenario also, we observe that BMP and MMSUP achieve a better accuracy because MAML is known to generalize well for unseen tasks coming from a similar distribution and not for unseen tasks coming from unknown distributions. So in conclusion, we have seen that the GBML family of algorithms assumes that tasks are sampled from a single distribution. So if you naively train on tasks from multiple distributions, their performance degrades. You could train multiple models, one per distribution, but this adds to the training time, and which is why BMP and MMSUP both train on a single model in a multi-distribution scenario and have been seen to outperform the MAML algorithm. We plan to extend this work for image segmentation, object detection, also in a multimodal scenario where the model should be capable of generalizing well on input tasks from different modalities. Thank you.